how Newton might interpret gravity was sufficient to permit us to fly from the Earth to the Moon. At any point, we might end up lost in the ticking hands of time, contemplating whether how we interpret it is only the tip of the fleeting chunk of ice on its head. His disclosure isn't a hypothesis. A key could open the ways to the secrets of the universe, uncovering a universe more perplexing and rousing than we at any point thought to imagine. How does Brian Cox's new hypothesis challenge our customary comprehension of time, and what are the possible ramifications for our impression of reality? Join us on a captivating investigation through the annals of time itself as we dive into Brian Cox's recently uncovered notable hypothesis on the nature of time in the vast universe around us. Secrets are ready to be revealed, and a portion of these secrets includes confusing concepts like gravity, which are fundamental pieces of our reality. Imagine an existence where time acts unusually. It can either slow down or accelerate. Additionally, the force that keeps us on the ground probably won't be what it appears to be. This is the domain of Albert Einstein's theories of relativity, where how we interpret time and gravity goes off in an unexpected direction. Albert Einstein, a notable name, furnished us with a new way of looking at the universe through his theories of relativity. His work established the groundwork for understanding how time behaves in various circumstances, particularly while traveling at very high speeds. Everything started in the mid-20th century when Einstein proposed two noteworthy theories, the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, changed how we interpret existence. In simple terms, it tells us that the laws of physics remain the same for all observers who aren't accelerating, regardless of their motion. This theory presents the possibility of relativistic effects, including the popular idea that time can expand or slow down under certain circumstances. One interesting thought experiment used to explain time dilation is the light clock. Imagine being inside a spaceship moving incredibly fast, nearly at the speed of light. Inside the spaceship, there's a light beam bouncing between two mirrors perpendicular to the direction of movement. According to the laws of physics, the speed of light is constant for all observers, so the light beam should seem to travel along a longer diagonal path. The time it takes for the light beam to travel should be the same for both the observer inside the spaceship and the one outside. However, since the path is longer for the external observer, it seems like it would take more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer moving relative to the stationary observer. In this scenario, time behaves differently depending on your motion. Understanding how things change when they move fast, known as relativistic effects, isn't just a theoretical idea. Researchers use huge machines called particle accelerators, like the Large Hadron Collider, to make particles go incredibly fast, almost as fast as light. When things move this quickly, we need to perceive time in a unique way to make accurate predictions and measurements. Albert Einstein concocted the special theory of relativity in 1905, and it changed how we view the universe, particularly regarding time and motion. This theory challenges what we might normally think. It says that the laws of physics are the same for everyone, regardless of whether they are in motion. This contrasts with our everyday experience, where we might feel that if something is already moving and we add more speed, it goes faster. However, Einstein's theory posits that there is a maximum speed that nothing can exceed, and that is the speed of light. From this perspective, events that seem to occur simultaneously for us might not appear that way for individuals moving nearly as fast as light. Another concept that arises from this extraordinary viewpoint is length contraction, which means that if something is moving, it appears shorter in the direction of its motion when viewed from a stationary point. Then, there's the famous equation, which demonstrates how energy and mass can transform into one another. This is crucial for understanding how tiny particles behave when they zip around superfast, and also for phenomena like what happens when atoms split in nuclear reactions. In reality, special relativity isn't just a fancy theory, it's something we use in everyday applications like GPS. When GPS satellites send signals to your device, they're moving, and as a result of this movement, time behaves a bit differently for them. If we didn't account for this time dilation effect in our GPS calculations, your navigation would be inaccurate. So, special relativity teaches us that time isn't the same for everything and everywhere. It heavily depends on how things are moving. This idea challenges our understanding of existence. It's like saying our normal perception of the universe is somewhat skewed. According to this special theory of relativity, time isn't fixed, it's influenced by motion. Several foundational concepts, such as the constancy of the speed of light and the connection between energy and mass, have been validated through numerous experiments. But there's more to enter. Albert Einstein's general theory of relativity from 1915 digs deeper into the relationship between gravity and how the universe is structured. It overturns the old idea that gravity is just a force that pulls things from a distance. Instead, it tells us that gravity occurs because space-time is curved or warped. It's like saying, hey, gravity isn't a mysterious force, it's just how things naturally move in the universe. According to Brian's understanding, general relativity means thinking of the universe as a four-dimensional fabric, combining 3 dimensions of space and 1 of time. In this framework, massive objects like stars, planets, and even us influence how space-time is shaped around them. This shaping is what we perceive as gravity. Imagine space-time as a big, stretchy sheet. When something heavy like the Earth is placed on it, it creates an indentation in the sheet. If you place something smaller, like a ball, near the Earth, it will move toward this indentation. This is similar to how objects behave due to gravity, not a strange force, but rather a response to the bending of space-time. General relativity provides a robust explanation for how things move in our solar system. For instance, it accurately describes the orbits of planets around the Sun, including how Earth follows an oval-shaped path. According to Brian, this differs from the old idea of gravity merely arranging objects, which struggled to explain how planets move as they do. The novel concept is that space-time is bent like a flexible fabric, which aligns better with our observations. A pivotal moment that demonstrated the undeniable power of general relativity occurred during a solar eclipse in 1919. Sir Arthur Eddington led a team to observe how light from distant stars bent as it passed near the Sun. According to the theory, the Sun's mass would cause the starlight to bend slightly. The observations matched Einstein's predictions, establishing the validity of the theory. Just as motion can change how we experience time according to special relativity, gravity also affects time. In areas where gravity is particularly strong, time moves more slowly compared to regions with weaker gravity. So, if you were near a massive object like a black hole, your clock would tick more slowly than one placed far away from this strong mass. General relativity introduces black holes, which are regions where gravity is so intense that nothing, not even light, can escape from them. The boundary surrounding a black hole is known as the event horizon, and it acts like a final turning point. Once something crosses this threshold, it gets pulled into the black hole with no chance of returning. Einstein's general theory of relativity has significant implications for how the universe is structured. Initially, he introduced a concept known as the cosmological constant into his equations because he believed the universe was static. However, when we discovered it is expanding, he referred to this as his greatest mistake. The idea of an expanding universe, based on general relativity, is a crucial component of the theory of the universe's origin, which explains how the universe began. Another significant concept from general relativity is gravitational waves. These are ripples in the fabric of space-time caused by extremely massive objects moving quickly, such as when black holes or neutron stars merge. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory directly detected gravitational waves, providing evidence for yet another aspect of Einstein's theory. Over time, scientists have conducted various tests to determine whether general relativity holds true, and each time, it has proven correct, whether by observing how planets move, the bending of starlight, or the detection of gravitational waves. While saying gravity is completely false may be astonishing, especially since we all experience gravity daily, in the realm of physics, it's common to discuss and explore different ideas. Researchers like Brian often challenge established theories, and in the realm of gravity, some test the conventional ways we think about this fundamental force. One idea that challenges conventional gravity is called modified Newtonian dynamics, MOND, which suggests that gravity behaves differently at low speeds, particularly in galaxies, without the need for dark matter. Rather than adding invisible matter, Mond suggests that gravity strengthens at low accelerations. The gravity debate also includes the mysterious concepts of dark matter and dark energy, introduced to explain certain phenomena in the universe. Dark matter is thought to make up a significant portion of the total mass in galaxies and galaxy clusters, while dark energy is believed to be responsible for the accelerated expansion of the universe. Both concepts arise from observations that do not align with our current understanding of physics based solely on visible matter. The interplay between gravity, dark matter, and dark energy raises important questions about the nature of the universe. For example, how does dark matter interact with regular matter? Why is the expansion of the universe accelerating, and what role does dark energy play in this process? These questions challenge scientists to rethink the fundamental laws of physics and the structure of the cosmos. As researchers delve deeper into these mysteries, they employ various observational techniques and advanced technologies. Telescopes that capture different wavelengths of light, such as radio, infrared, and X-rays, provide insights into the behavior of celestial bodies and the influence of unseen forces. Furthermore, particle physics experiments aim to detect dark matter particles directly, potentially unraveling one of the universe's greatest enigmas. The quest for understanding gravity and its relationship with time and space continues to inspire scientists. Theories are constantly being tested and refined, leading to new discoveries and a deeper comprehension of the universe. For instance, the recent detection of gravitational waves has opened a new window into astrophysics, allowing scientists to observe events that were previously hidden from view, such as the collisions of black holes and neutron stars. As we expand our knowledge, it becomes increasingly clear that our perception of reality is just a fragment of a more complex and dynamic universe. The concepts of time, gravity, and the fabric of space-time are not merely abstract ideas. They have tangible implications for our understanding of existence. Each breakthrough in this field prompts us to reconsider our place in the universe and the fundamental principles that govern it. In conclusion, the exploration of gravity, time, and the universe is an ongoing journey that challenges our assumptions and expands our horizons. As we continue to question established theories and investigate the mysteries of the cosmos, we may find answers that reshape our understanding of reality itself. The interplay between these elements not only informs our scientific knowledge, but also invites us to ponder profound philosophical questions about existence, the nature of the universe, and our role within it.